Hi, I'm David Rierick. I'm the project manager for the Navy Mantech project Automated Metrology for Structural Assembly. This project was executed by the Penn State Electro-Optics Center at the Applied Research Labs, a Navy Mantech Center of Excellence. During this project, a collaborative team including General Dynamics Bath Iron Works, Direct Dimensions, and the Penn State Electro-Optics Center developed and refined an autonomous metrology technique for capturing large volume structures with high levels of accuracy using targetless photogrammetry. The goal was to enable lower cost in-process accuracy checks during different phases of ship construction.
I'm Thaddeus Morar. I'm a research engineer. I worked on the photogrammetry and the software automation processing.
My name is Jim West. I'm a research engineer. I worked on the imaging and system engineering part of this project. To begin the data acquisition and metrology process, the user only has to complete a few straightforward steps to use the Skydio X2D drone. 5 to 6 coded targets are placed on the structure that is to be inspected in order to scale the point cloud and align it to the CAD model. The coded targets are placed in COTS magnetic nests that align to punch marks in the steel. Targets are placed either on previously surveyed points or new locations can be established and surveyed after the Skydio 3D scan process is complete. The Skydio drone is equipped to handle most of the data capture autonomously. The first step is to set up and launch the drone near the structure. Then it is piloted to obtain the desired observer view. Next, the floor, ceiling, and pillars are set to define the volume for the 3D scan and the boundaries for flight. With the boundary set, the Skydio flies to explore inside the volume and determines the rough geometry of the structure and the path it will follow for photo capture. After exploration, the Skydio hovers and the estimated flight time, number of photos, and number of battery swaps is displayed on the controller. Final settings are completed by the pilot and the 3D scan process is started. During the 3D scan, the Skydio flies by itself around the structure at a specified standoff distance and uses AI to collect photos at the right position and pose necessary to achieve the correct image overlap for photogrammetry. Minimal pilot interaction is required during the 3D scan. The total time to perform a 3D scan of the shipping container is about 30 minutes and about 700 images are collected. Larger structures like inverted structural assemblies for ships take about an hour and require 2 to 3 battery swaps. Each battery provides about 30 minutes of flight. If a battery swap is needed, the Skydio will automatically land at the takeoff position. After swapping batteries, the Skydio will launch and resume the scan where it left off. At the completion of the 3D scan, the Skydio lands and the micro SD card containing the photos is removed.
A demo application was created to provide the user with a straightforward interface. This wraps all the photogrammetry and calculation processing into an easy-to-use front end. After acquisition, we start the process to transform it into a partial 3D digital twin by performing photogrammetry. We start by uploading the captured images to the server. Next, the coded targets are located in each 2D image. The coded targets we are using are ring automatically detected or RAD targets. A dual ring system was selected over a single ring for robustness to avoid false detections. These coded targets have been previously surveyed, generating an X, Y, and Z coordinate in the same coordinate system as the captured structure. The surveyed coordinates of the RAD targets are used as ground control points to scale and align the point clouds to the CAD model. After this, the alignment process is started. This registers each camera into a 3D space around the structure of interest and determines how the cameras are related to each other. For each camera, not only is the location calculated, but the camera orientation is determined as well. This includes the yaw, the pitch, and the roll. The alignment process results in a sparse point cloud with a rough outline of the structure and camera positions around the structure. The last photogrammetry step is to convert the sparse cloud into a dense cloud which is the longest stage of the pipeline. This step is known as reconstruction or densification. The result is a dense cloud which can range from tens to hundreds of millions of points. In addition to a colored point cloud, we also have normal vectors associated with each point. This vector can be thought of as a direction from the point to the camera that captured it. This can allow us to determine additional information about the point for later calculations. For a true digital twin, you would probably want to generate a mesh or textured mesh from this cloud. At this moment, our downstream calculations are based solely on the dense cloud, but there may be potential for using a textured mesh in the future. After the dense cloud has been created, we can then calculate the deviation between the planned CAD model and the as-built structure. There's a one-time configuration when inspecting the first structure of each type to generate a recipe. We upload the original design of the structure in CAD format, as well as the dense cloud we just created. From these two items, we create a deviation map or heat map over the entire structure, showing how far each point is in the cloud from the CAD model. Part of the heat map calculation includes the normal vector associated with the dense point cloud. This allows for an additional verification stage. For a thin shell plate, this determines on which side of the material the point lies and can be treated in the right way. A second set of calculations is also performed using a previously provided list of points of interest, or check sheet. These points are locations where critical measurements around the structure are required. For the location of these points of interest, planes are calculated from the surrounding point cloud. This could be a single plane, in the case of a level shot, to discover how level the deck plate is, or it could be the intersection of three planes which form a point. From these planes, the associated points are extracted for comparison to the survey points or for direct use. These extracted points can also be compared back to the heat map if desired.
The motivation of this project was to develop an automated process that could be executed by persons without extensive knowledge of metrology practices. Instead of trained survey crews, we were targeting ship fitters and other tradespersons. So, by developing an automated method to capture and process data, the expectation was that we could increase the availability of in-process accuracy checks to help reduce rework and improve throughput and also reduce cost. After research into different available technologies and systems, the team really focused on leveraging targetless photogrammetry techniques to develop a low-cost solution. This work really involved many aspects, including developing planning tools, researching automation platforms, and understanding how individual pieces could be augmented to improve system accuracy. Results of this project showcase the technology's ability to deliver highly accurate point clouds that can be compared against a 3D design model to generate a heat map that displays deviations of the as-built structure without the need for significant user involvement. The best part about this technology, hands down, is that it uses a unique combination of off-the-shelf hardware and software components, including the Skydio X2D drone that has built-in automation and does not require an experienced pilot to operate. By combining these components, the team created a scalable technology package that is both low cost and simple to deploy, making it easier to transition to industry and commercial partners.
At the start of the project, the measurement technology to use was not defined. We needed to find a technology that would meet accuracy requirements, be usable by minimally trained personnel, and be automated to the greatest degree possible to reduce labor. Trade studies were conducted to evaluate the state of the art. Technologies considered included LiDAR, laser scanners, laser trackers, structured light, and targeted as well as targetless photogrammetry. Several technologies were eliminated due to accuracy, but the ability to automate data collection became the greatest challenge. Ultimately, targetless photogrammetry was identified as the technology that would best meet the objectives. Some testing in a shipyard with a cable rig and a Canon camera confirmed that the required accuracy was possible. The initial plan was to put a DSLR camera on a drone, but the size of the drone required was not going to be acceptable for use in the shipyard. The timing was good because Skydio had recently introduced their X2D. The Skydio X2D was selected for this application due to its small size, Blue UAS certification, and its ease of use. The AI-based obstacle avoidance and 3D scan allows a minimally trained user to capture data.
An initial photogrammetry study was conducted limited to COT systems out of the box. Emphasis was placed on accuracy and minimally targeted or targetless systems. A third-party photogrammetry service provided initial testing data of a shipping container that looked promising for photogrammetry. In general, we found photogrammetry to be scalable depending upon a number of factors, including camera sensor, distance from the structure, and image overlap. We evaluated several software packages. Some software was not considered due to the country of origin. We ended up selecting two separate software packages, Zephyr and Reality Capture, due to the flexibility, overall performance, support, and potential for automation. As a side note, Zephyr is based in Italy and Reality Capture is owned by Epic Games, which is based in the US. After further testing, we focused on Reality Capture because of higher performance and scriptability for photogrammetry. We also performed a trade study for cloud CAD measurement software. We reviewed multiple options. Our requirements were we needed to be able to process large point clouds, needed capability for automation, instrument data and CAD compatibility, ability to mitigate ancillary items for temporary items left on or around the structure but not part of the CAD model. We ended up selecting Polyworks since it was the most responsive for large point clouds of greater than 100 million points.
Accuracy was tested using a shipping container. We first generated a high accuracy ground truth mesh using a laser scanner and laser tracker. Our point clouds were then scaled and aligned to the mesh using the coded targets. From there, we generated histograms representing the deviation of all the points in our cloud from the mesh. The accuracy of our results exceeded the expectations. The histogram bias was on the order of 0.1 millimeter and indicates excellent scaling and alignment using the targets. 94% of the points are within 10 millimeters of the ground truth, and the median absolute deviation was only 1.3 millimeters. The effect of point noise is further reduced by visualization and point extraction techniques. The effects of point noise are essentially averaged out.
As the project manager, my goal is to support testing of this new technology in the actual shipboard environment. We look to ensure it can be integrated into our production processes. It is also to look towards future applications where we can expand these processes. We will support other areas of new construction and sustainment activities.
We need to be highly accurate, on time, every time. The motivation for this project was to improve and accelerate our current survey and photogrammetry processes. We work in the inverted and right side up construction stages. The idea of a drone capturing discrete points, targetless, is definitely an advantage. Not to mention the ability to collect 3D data where there is limited line of sight or inaccessible areas. Our production organization is looking for us to deliver as-built data quicker so that they can assess, make corrections, and ultimately move the product to the next stage on time.
Targetless photogrammetry, executed with the support of a drone, minimizes the need for transportation support to complete the job. This advancement eliminates the need for aerial lifts on land and the combination of barges, tugboats, and aerial lifts while on the water. In both cases, it would improve worker safety, save us time, and lower costs. In the future, we are evaluating this technology for rapid damage assessments, 3D ship measurements while on the water, and to support repairs or planned structural upgrades.
This could be a game changer. There's no question about it, because the idea here is that this is relatively low cost equipment. It's always going to improve. I mean, we all know the improvement curve of something like drones is moving quite rapidly, as well as cameras, as well as computers as it relates to processing the data. So all of this is moving very rapidly for many other reasons besides this one project, and we get to take advantage of that. So we're very bullish on where this could go, how helpful this could be, not just to this application, this one application at BIW, but also many other applications within the U.S. Navy and other, as well as commercial shipbuilders, as well as, large industrial applications. We're really excited about where this is and where it's going, where it could go, and we're thrilled that the Navy has invested in this through its ManTech program, and really feel like there will be a payoff, not just for this one project, but for really what could be quite groundbreaking going forward.
The workflows created by this project were designed to be totally technology agnostic. This allows different capture methods, cameras, and systems to be swapped out based on the end user's needs. For instance, A drone could be replaced with an overhead cable system for low-light indoor applications requiring higher levels of accuracy. The team has also identified potential improvements to the Skydio platform that could enable inspection of increasingly complex structures. To facilitate adoption, the project team has developed a transition package that can be provided to DoD and other commercialization partners as requested for dual-use applications. While the technology used for this project has demonstrated excellent results, future hardware advancements could enable the capture of additional and more complex use cases with even higher levels of accuracy.